Normally you think of line balancing to create assembly lines. Sometimes you use line balancing to create temporary systems. Lin-Lithi Medical, this scenario is a good example of that application of line balancing. Let's look. Lin-Lithi Medical provides on-site health screenings for other organizations and has been hired by the City of Baltimore to conduct the annual health screening for all 250 of Baltimore's bus drivers. The annual health screening for a bus driver consists of the following tasks. All right, so you can see that this is a line balancing problem shaping up here because there is for each driver a series of things that need to be done. There's some precedence relationships, and then there is an estimate of how long each task takes. What other information do we have? Lin-Lithi has arranged to screen all 250 drivers during one 5-day week. Thus, Lin-Lithi must complete 50 health screenings during each 10-hour days. To perform the health screenings efficiently, Lin-Lithi Medical will set up its operation as a product layout in which the drivers move from station to station until all the tasks of their individual health screenings are completed. Please complete the line balancing to design the most appropriate layout using longest processing time rule. So you can see this particular problem. What this is a project actually to screen 250 bus drivers, but it is a line balancing problem because you will be designing the stations at which the bus drivers will receive the following services. And you can see all that information, task information there, precedence information, duration, some mention of overall output, some mention of a decision rule, and some mention of operating time. That makes it a line balancing problem. All right, now, what are the questions? Well, first off, what is the cycle time of Lin-Lithi Medical's layout for the Baltimore City bus driver screenings? So, cycle time equals operating time divided by demand. That is to say, how long you want to run the line, what time interval, and then what you expect the line to produce in that time interval. And we were told the two numbers we need to get this reading because they said they must complete 50 health screenings during each operating time, each 10-hour day. So if the operating time is 10 hours, then the output or the demand on the system is 50 total completed screenings, so that's what, 0.2. And actually that does answer the problem in that it just asked what the cycle time was. 0.2 is the answer. Yes, for a fact, but notice what else I wrote. You say, okay, cycle time. So each station will have how long to do whatever task assigned to it. 0.2, it's 0.2 hours. I wrote hours. Whatever OT was in, the cycle time, the first time you calculated, that's what it's in. Okay, now, that is the answer. I would not leave it there. I would not leave it there. It answers that question the way that it's stated, but we kind of know that we're going to have to go ahead and balance the line. In a line balancing problem, first you calculate the cycle time, but don't leave the cycle time until you have it stated in check the same time units as your duration data. Notice that here this information about the various tasks at the station are in minutes. That means we need a cycle time that's in minutes. Not a problem. 0.2 hours, if I multiply that times 60, reveals it's the same thing as 12 minutes. That is what I will need to move on further with this problem. Okay, but at any rate, that first question is answered. What's the next question? Next question. What is the theoretical minimum number of workstations that Lin-Lithi Medical might have to staff to support this cycle time? All right, that's a formula. Capital N for number of stations, but we're talking about the theoretical minimum. Couldn't get any better than this. That is the sum of the task times divided by the cycle time. That is the formula. Oh, all right, now we were just commenting, we know what the cycle time is. The cycle time is 12. I mean, I could fill that in. But the sum of the task times, I mean, what do I put in the numerator? Oh, I need the data back. Because I need to add up all of these numbers right here. I add 5, 7, 5, excuse me, 5, 7, 3, 10, 4, 8, and 10. And what I got was 47, which is an interesting reading all by itself. 47. That's the sum of the task times. That's how long it would take to completely screen one bus driver if there was just one medical professional working with them, completing all the tasks all by themselves. Okay, so anyway, we needed it for that formula. I put the 47 here. 47 divided by 12 on my calculator comes out a little messy, 3.91 some odd. Remember, with this formula, you always round up. You want to reply in a whole number because you're talking about number of workstations. And when you get decimal places from the formula, you always round up. Now, you're looking at this one and you're going, well, it's 3.91. I mean, duh, why wouldn't I round up? Oh, sure, this time it turned out such that you would naturally round up anyway. But those funny looking brackets, what they mean is always round up, always bump it up. So even if it was 3.05, you still would have replied that the theoretical minimum number of workstations is 4. 4 workstations. All right, so we know that no matter how we group these tasks, we can't get all these bus drivers screened in anything less than 4 workstations. That's just something we now know. Now, what's the next question? At which station will task D, the lung function test, be completed? And then, right after that is the question, at which workstation will task F, the pulse stress test, be completed? These two questions obligate us to actually design the line, because we'd have to design the line in order to locate those tasks. Oh, now that means we have to conduct the line balancing algorithm. And you can remember how to do the line balancing algorithm if you can remember. Now in the note frame, this full header has been included. Station, time remaining, eligible tasks that will fit, and assigned. Now, actually, before we start designing the line, there is one other thing that we really ought to do. It's not strictly mandatory, but I wouldn't work a line balancing problem without doing this. I'm going back to the original data. I'm backing up. I want to draw a precedence diagram. I want to illustrate this table of data because it's easier to work with the illustration than directly with the data. Okay, so I want to draw an illustration of these tasks and how they relate to each other. How do I do that? I scan the list of tasks. First, I'm looking for all the tasks that don't have any immediate predecessors, and I see that there's 4 of them here. All right, I'm going to draw them. Well, I'm going to draw a symbol of them. This is task A, this is task B, this is task C, and this is task D. Okay, fine. Now what? Now I want to add the other tasks. Task E has task C as an immediate predecessor. That means that you cannot draw the blood sample until you have finished the blood pressure test. Draw that. Here's C, the blood pressure test. We say when you're done with that, you can go on and do this, right? Task E, the blood sample. Now, all right, then that one's done. There's only 2 other ones to add then here. Okay, the pulse stress test has 3 immediate predecessors, B, D, and E. You can't do the pulse stress test until you have done the hearing test and you have done the lung function test and you've drawn the blood sample. So, B, D, and E, why don't I put F here? This is the pulse stress test, F. You have to finish E, you have to finish D, and you have to finish B. When those 3 things are finished, then you can do that. Then there's only one other one. It says G, doctor's consultation, has A and F. Okay, so until you've done the vision test and gotten all the way and completed the pulse stress test, then you can talk to the doctor. I think that from my diagram, the easiest thing would be to put that last consultation here. When that's done, and see, I'm going to connect upwards, this is done. Then the entire mini project, if you will, is completed. Okay, so this is just a visual representation of this data in essence right here. before we leave, again, we're just illustrating, we haven't determined anything. Something that's really handy is go ahead and note, if you've drawn the precedence diagram, go ahead and note the durations next to each one of the tasks in the illustration. So A is 5 minutes, and the funny thing is it is right over here where I drew it next to that fact anyway, but I'm just putting a 5. And it's a reminder that one's 5 minutes, B is 7 minutes, C is 3 minutes, D is 10 minutes, so I'm going to put that there. E is what, 4 minutes? I'm going to put a 4 in here. F is 8 minutes, so I'll put the 8 there where F is at, and G is 10 minutes. Okay. All right, now that's just a tool. Why don't we actually do some line balancing? To design an assembly line, you begin at the first workstation. Oh, okay, so we're at station 1. We're at station 1 and we have not assigned any of these tasks. Nobody's done anything yet. That means that time remaining, put the cycle time. 12 minutes. There's a 12-minute budget at this station, right? It's remaining to be used. Now, eligible tasks. We'll look at the diagram. None of this has been done. Who could you potentially pick up and start on? Well, what you're actually looking for at this point is you're just looking for everybody, and you could see it over here as well. You're looking for everybody that doesn't have any immediate predecessors, because those are all things that could be done initially. On this one, you know, there's 4, A, B, C, and D. List them. You could assign any of those right now to the first workstation. Eligible tasks that would fit, that's just where you're checking that each one of them would fit inside of 12 minutes. And seeing how this is a brand new workstation, they all would have to. Which means that now you have to pick one. That's what assigned means. Pick one. How are you supposed to pick between the 4 of them? That's why they mentioned longest processing time. Oh, right, a line balancing problem always has to have at least one decision rule, so that when there is a choice, you know how to pick one of the tasks for the assignment. This particular decision rule is pick the longest one. All right, well, A is 5 minutes, B is 7 minutes, C is 3 minutes, and D is, oh, D is the winner. D is 10 minutes. We're assigning D. D gets the assignment. Okay, so already we know that D, the lung function test, will be done at the first workstation, which now we've just barely started this line balancing problem. We have not finished it by any stretch of the imagination, but actually I could answer this question right here. First workstation, because it asked about D. Okay. We better keep going though with the problem. Now, D is 10 minutes long. That means that there is 12 minus 10, 2 minutes remaining at this station. Now, who is eligible at this point? You know, if we were looking for something else to do. Well, A, B, and C, we're still trying to find a home for. We have done D. It is connected to F, but there's no way that you could start on F because it's waiting on some other tasks as well. So your sort of menu of choices is still A, B, and C. A, B, and C, will they fit? Well, there's 2 minutes remaining now. The smallest one is C, and it's 3 minutes long. None of these will fit. Tells us that this station is done. The first workstation will just do the long function test. That's what we've determined. All right, now time for basically a fresh workstation. Station 2. Where we get to start over with 12 minutes. We're still looking for a home for A, B, and C. This is a fresh workstation, so any of those should fit. Just copy it over. So, assignment. We have to use the longest processing time again. I'm looking back at the data, and I see that B is the longest of the 3 that are remaining. It's the longest. It's 7 minutes long. It's gotten the assignment. Just because it's done, you can't go on to F because we're still stuck here. So that means that there's nobody new to add in terms of eligible tasks. We have reduced the amount of time remaining. B was 7 minutes long, so 12 minus 7. There are 5 minutes left, and we are still looking for a home for A and or C. And I'm looking at the data, Let's see, A is 5 minutes and C is 3 minutes. Each one of them would fit inside the 5 minutes. We pick the longer one. That's the rule. Okay, that's A. All right, so this second workstation will also do the vision test. Great. Now 5 minus 5, that means we're out of time at this station, which is actually perfect. It has exactly 12 minutes worth of work for every 12 minutes that it's given. So we close that station. Open up a fresh station. Now, at the fresh station, there's 12 minutes remaining. We have, and we're still trying to find a home for C. Now, let's see if there's anybody else that has become eligible. Because we did find a home for A, so A is done, B is done. A is done, but you can't go on to G because, again, we're waiting on F. You know, at this point, we have to go all the way back and catch up with C. C is the only thing that's eligible, which makes this easy because C automatically gets the assignment. C is just 3 minutes long. Okay, 12 minus 3, there's 9 minutes remaining. All right, now C has a home. It'll be done at the third workstation. Now who's eligible? Let me use the proper color here for marking it off. E becomes eligible, right? Yes, when C is finished, E becomes eligible. Oh, I think, yeah, E is actually the only thing that's eligible because everything else is kind of jammed up. Okay. Then E is eligible, the only thing eligible. E will fit. E's not very long. It's only 4 minutes long, so E gets the assignment. It's only 4 minutes long. So 9 minus 4, we have 5 minutes remaining. So we have a good chunk of time still remaining at this third workstation. E's done. Who is eligible now? Actually, at this point, F becomes eligible because by now we've done B, we've done E, and we've done D. And that was the problem with F, the pulse stress test. All three of those things needed to be assigned first. But now for the first time they are. Now for the first time they are. So F is eligible. That's good news. But we check the data and it says 8 minutes. F is 8 minutes long. It's not going to fit. Oh, all right. Even though we have 5 minutes to spare at this station, we have to close it because there's nothing else that's going to fit. Open up another workstation. Now we're back to 12 minutes. F is still the only candidate. F automatically gets the assignment then at that point. Okay, it was only 8 minutes long, so let's see, 12 minus 8, there's what, 6 minutes to go at this station. And I'm looking at the tasks, and there's only one other task that needs an assignment, and that's G. And finally, G is ready to be assigned because A and F have been assigned before it. But G is 10 minutes long. So, again, we're going to have to give up on this workstation and add one more workstation, workstation 5, fresh budget of 12 minutes, to find a home for G. That is where G would be done. The one last task, the doctor's consultation, at the 5th session. Oh, all right, so this is our design according to what Lin-Lithi requested. It is a product layout with 5 stations. There are where each of the tasks are going to be done. And what was asked, well, we already answered that. We saw that right away. D will be done at the first workstation. So one other question, at which station will task F, the pulse test, be completed? Just find it. F will be completed at the 4th one. That's where it got the assignment. Okay. 4th workstation. The scenario doesn't pose any more problems about our design. So at that point, we've completed it.